essentially all the interacting effects are identified as follows: the kinetic energy, essentially the kinetic energy of non-interacting and kinetic energy of the interacting. Similar way also the Coulombic or Hartree-Fock energy plus exchange, also we can write it as the Hartree-Fock plus the non-interacting and also the interacting. Okay. So, where this EC interacting or this E kinetic non-interacting and also the E kinetic interacting are correlation energy. So, this is the correlation energy and this is the non-interacting and correlating kinetic energy and this is the correlating kinetic energy. So, essentially this is the correlation energy, non-interacting kinetic energy and this is the interacting kinetic. So, essentially what we are doing is total kinetic energy we are writing into two terms. One is the non-interacting term, another is the interacting term. Similar way also the total energy in the these two, this Coulombic energy and also the exchange energy, also we are writing as a kind of this Coulombic energy plus exchange plus the correlation, okay, in the interaction. Okay. So, now if you regroup all the interacting terms together as a single term called the exchange correlation. So, essentially we are just writing out all the the non-interacting terms as a kind of the exchange correlation energy. So, it will be Ex plus EC interacting plus E kinetic interacting and we are writing as Ex plus EC. So, this interacting the interacting energy and also the interacting kinetic energy we are writing as this EC, Ex plus EC and you are writing as EXC or you are writing as a exchange correlation energy, okay, which is the interacting, okay, and non-interacting we are just using to find out the kinetic energy, okay. So, kinetic energy plus non-interacting Coulombic energy plus exchange energy will give you the of course along with the external energy will give you the total energy. So, the total energy becoming the electronic energy, kinetic energy of non-interacting electron. This is the external energy nothing but the interaction energy between nuclei and the n number of electrons, and this is the electronic the repulsion energy. If we write similar way how we write it as a kind of the Hartree-Fock case, and this is the exchange correlation energy which is not known, which is the interacting part, okay. All these are non-interacting, okay, and this is the interacting, okay. The first three terms are relatively easy one to calculate, while the last term is unknown and this is the subject to the approximation. This is the main part in the DFT and where this exact form of this exchange correlation part is not known. So, there are different functional forms are used and this functional can be again approximated by using the AIML methods. Here comes the main the area of work of AIML in the DFT base, in the development of DFT. Okay. Finally, the repulsive interaction energy between the nuclei will be added as a constant within the one Oppenheimer expression to get the overall energy. Okay. So, this is the electronic part. Now, you need to add the electronic repulsion energy, so that you get the you need to add the nuclear repulsion energy, then you get the total energy of the system. Okay. So, if we now, so in the exact sense what we have the real system is a interacting system. It will have the kinetic energy, external energy, Coulombic energy and also the exchange energy. In the case of the Kohn-Sham case, what essentially he is doing, as I have said in the earlier slides, essentially is decomposing into interacting and non-interacting, so that you can track this interaction between the electrons. Okay. So, essentially we are considering that electronic kinetic energy has two parts, one is the non-interacting, another is the interacting. External part remaining same as in the case of the Hartree-Fock case. External case is as if it is the interaction, the attraction between the nuclei and the electrons, where electrons are treated as a non-interacting one. And here also the electron-electric repulsion, again we do it is a kind of a Hartree-Fock case. Okay. And now, this exchange part again we are writing into two terms, okay, exchange and correlation. So, essentially what we are getting is now all of these three terms are now non-interacting and this is the interacting. So, non-interacting term we can easily get it, we can easily find it out, but only problem is this interacting or the exchange correlation energy. Okay. So that's why we can also write the corresponding Hamiltonian operator, the non-interacting kinetic energy, this external energy operator, then also this operator for this the Coulombic energy, and also the operator for this exchange energy. Okay. And also we can write it out. So this kinetic energy is nothing but minus of, if you write it in atomic unit, minus of half del square plus, and all these together we can write it as a U effective. So all these operator we can write all the potential operators, we can write it as effective. So this is the effective potential including 3 potential term, and it manipulates the ground state electronic density of the non-interacting system to be identical with that of the true interacting system. Okay. So essentially we can say that, let's say you have got any interacting system, then we are considering at that in any electron system where each electrons are interacting. So it has got the kinetic energy plus the potential energy, where you have got the energy exact in terms of a functional of rho r and exact energy. But what we are doing here, we are writing one electron system. Each of them are behaving independently without the interaction from the others. We can say that it's kind of the mains are replaced as the robots, and these robots are individual, they are not interacting. Okay. So but this interaction part, so first we calculate the easier part taking as a non-interacting, then the difficult part we are writing as a kind of the exchange correlation, and this exchange correlation now we need to use some kind of the approximation, all the approximation in the exchange correlation. So that is essentially the DFT method. Okay. So we are considering n number of systems decomposed into a system containing n electrons are decomposed into n number of non-interacting systems, but the interaction part, so that it depicts the real one given by the penalty as this exchange correlation energy. Okay. So here a complex n people system is replaced by an artificial n robot systems. The auxiliary system is now easily and fully calculable owing to its simplicity, and if the exchange functional where the AIML is useful in a big way to find it is accurately known, and the electron density is the same for both the systems. So that you just now you match the electron density in the exact the actual system and the electron density of the non-interacting system. Okay. So where you just vary the some parameter so that you get the exact density, and at the same time also you know that if you know the density we can get all the other parameters. Okay. So that is essentially the DFT methods. Okay. So essentially we are decomposing into interacting and non-interacting. All the non-interacting part is easy to do it. Okay. And interacting part, it's you are just using it some kind of the modification of the parameter so that it depicts the actual density. Okay. And that density now we can use it as a main variable to find out the other properties. So what are the energy term? Now we can easily get it. So some of them are non-interacting. If they are non-interacting, then we are just writing the wave function as a kind of a sum of the basis function. Okay. So basis function are kind of a non-orbital type of function, or it can be some of the plane waves. Okay. So this non-kinetic energy is easy because you know the sum of all the basis function with this minus of half del square. So kinetic energy non-interacting is easy. Okay. Now for the external energy, again also we can write it in terms of the basis function using the external the external Hamiltonian component, or we can say that the potential component for the external one, or the interaction energy between the nuclei and electrons. Okay. So again this parameter is known, and these values are also known from the basis function. So this is also easy to calculate. So you can write it also in terms of the density. Okay. So here also we are writing in terms of the, but this kinetic energy part we are not writing in terms of the electron density, or writing all the other terms or effective terms in terms of the density. So first part is the external part. Similarly also we are writing the Hamiltonian part also in terms of the so this is the UH operators, and the total energy also should be functional of this of the density. Okay. So here also you can write it in terms of the density. Okay. Similarly also exchange correlation energy, as we have done also, but we don't know the exact formulation of this. So but we can first exchange energy we can easily write it by changing the position, and we can get it by force center integrations. Okay. But the correlation energy is a little bit difficult, and also you need to know the idea behind this finding the correlation energy. So correlation energy, as I mentioned, electrons having two different spin can stay in the same orbital, but electrons are same all negative charge, so they will repel. Okay, so they will try to avoid. Okay, so that comes the correlation energy, and this correlation energy we don't get it if we use a average potential kind of approximation. We do it in Hartree-Fock method. Okay. So the two electrons with different spin can occupy the same orbital, however they repel each other because of the same negative charge they have, and this is the electronic correlation, and it is also result in less overlapping of the electron density because they don't want to stay together, generating a small attractive energy. Okay, and this is the unknown n electron effect that was missed in the Hartree-Fock method and is subject to the approximation. Okay, for materials at typical electron density, the correlation energy is much smaller than the exchange energy. However, at very low electron density, the correlation energy becomes very important, since the exchange interaction becomes less active in this sparse electron density. Okay, of course, this correlation energy also will be there if you have the rare earth kind of atom elements, or if you have some of the oxides of the transition metal also. The correlation energy effect are there. Okay, the exchange correlation energy can be viewed easily with the introduction of the exchange correlation hole in an electronic system. Okay, how this hole looks, I will show you. The presence of n electron at R discourages the approach of the other electron around it, and as a result there is an effective depletion of the electron density, namely the exchange hole. So due to this effect only, there will be some kind of the depletion of the electron, and which we term it as a depletion of electron as a electron hole, and which has two components, exchange and correlation. Let us say if we look at the hole density, so essentially exchange, let us say if you have two electrons, so the hole density will be less due to the exchange will be in the middle, but they will be of same type, same sign. But in the case of the correlation, their spin are too different, so it will be kind of this the hole density will be different around these two the two electrons having two different, and the hole will be the correlation hole will be mostly in the middle. So what essentially correlation hole it is not giving total energy, it is not changing. What it is changing, that it is just changing the shape of this exchange hole, or that will also change in the overall the electron density. Okay, so that electron density change due to this correlation hole, because this gives you this antisymmetry. So the overall the electron or the hole density looks something like this. Okay, so the electron density also will be different. So this distortion of the electron density take up as a kind of this exchange correlation energy. So unlike the exchange hole, the correlation hole form in both positive and negative direction, as I showed. This is in the positive direction, this is in the negative directions, because of the correlation between two electrons with two opposite spin, and it does not contribute to the total size of the exchange hole, but what it does, that it change its shape, as I mentioned. So this is the total shape of the exchange correlation hole. Okay, so one side is less, another side is more. Okay, so that's this distortion in the charge. So this gives you the distortion in the charge density around two electrons having different in spin. Okay, so how do we do this exchange correlation hole energy? Again, the local exchange correlation energy per electrons, because you need to look for per, that means between two pairs. Okay, the electrostatic interaction energy of the electron at R with the exchange correlation hole density. Okay, so essentially two electrons gives a single the exchange correlation hole energy, so we need to divide it by 2. Okay, so this exchange correlation energy between two electrons having two different spin, but they are very close. So in that case, it is given by this expression. That means the hole density at two positions divided by their distance. Okay, then the exchange correlation energy functional is the integral over the whole space of the density multiplied by the local exchange correlation density per electron. So essentially, the overall energy also we can write it as a kind of the quantum mechanical integral form, taking this as a the operator. So you get the overall exchange, the total energy, total exchange correlation energy as a function of the charge density using this hole operator. Okay, exchange correlation hole operator. So this exchange correlation hole operator is not known, but essentially we can some of the cases we can get that the total amount of exchangeable hole is subject to the sum rule, which equals exactly the 1 electron as expected. So essentially between two electrons in a same orbital having different position, so it should be minus hole is for the electron it is 1 if you have got 1 electron, but if it's hole then it should be minus 1. So in the Hartree-Fock method only the exchange hole is fully considered, but in DFT both holes are fully accounted for in the exchange coordination function, but only in the approximated formulas. Okay. So the concept of this, so essentially this concept will help you to determine what should be the exchange correlation functional form, okay, and which we are after, because we don't know the exact exchange coordination functional form. Okay. Concept of this exchange coordination hole and the sum rule like here and other provide guidelines for construction of the exchange coordination functional. So there are n number of functionals are there, more than 100, but the numbers are going day by day, are reported with various accuracy and computational cost. The most popular and generally used functionals are the local density approximation, okay, and the generalized gated approximation and the hybrid. Okay. So we'll just touch upon all this, the LDA and GGA method. Okay. So now before we go to that, essentially we need to say what are the contribution for different component in the of this the interaction. Okay. So first is that in the DFT sense we have got the kinetic energy we are writing as a non-interacting electrons. Okay. Maybe let us say that the total energy is minus or let us say minus 2.90 Hartrees. Okay. Out of this the interkinetic energy is plus 2.86. Energy nothing but the electron, the interaction energy or attractive energy between electrons and nuclei. So it should be negative. Hartree energy, that means electron repulsion energy is plus 2.049, and exchange correlation total energy giving minus 1.04 Hartree. Okay, including two components of exchange energy. So exchange about this exchange is minus 1.025 Hartree and correlation energy around 0.024. So if you look at this, mostly the external of the totals, and this is which is negative. And then you have got the Coulombic interaction or Hartree type of interaction, which is positive, kinetic energy is positive, and exchange part is negative. So that overall you get the minus 2.94. Okay. So the percentage wise we can say that exchange correlation all is generally less than 10%, but this energy dictates the most of the crucial materials property. So we need to look for this exchange correlation energy. So exchange energy cancel one half of the Hartree energy, and the electronic correlation energy that are only about let us say correlation energy is only 0.3%. However, the exchange correlation energy total around less than 10%, but among these the correlation energy is only 0.3%. However, exchange correlation energy is actively involved in the what are the changes happening in the atomic, molecular or solid system, and it crucially determine whether what are the what crystal system is stable, either BCC or FCC is stable, an array atom prefer a top or a hollow site or a metal surface, and whether a magnetic materials become ferromagnetic or antimagnetic. So all the magnetic and electronic property have got big effect on this electronic correlation and all. Okay, though its contribution is very less, but it dictates some of the very crucial property, basically in the magnetic property and also the band gap and all. So if you look overall case energy versus atomic distance, so we get first the Hartree energy, then we can use the Fock approximation further down. Okay, then the exact what are the ground state energy is here. Then, but if we use density function theory, we come closer to this because we are considering the correlation energy. So this is the correlation energy, and this difference between Hartree and Hartree-Fock is the exchange energy. Okay. So DFT finally covering all energy terms resulting in the lowest curve like here, and approach closely to the exact value. Note also that the energy difference between the Hartree and Hartree-Fock methods represents the exchange energy, while the energy difference between the Hartree-Fock energy and DFT methods represent the correlation energy. Therefore, having an accurate exchange correlation energy becomes a key factor for the successful operation of the DFT. So this main factor is this exchange correlation function, how the function is with respect to the density. Okay, and there comes the AIML. Okay. So this is the local density approximation. What does it say? That the What we do that the complex system is transformed into many pieces of uniform electron density with different values. Let us say a picture of this. So, we are just dividing into very small pieces, and within the pieces we are saying that there is no change in the density. So, let us say one piece here something like this, there is a similar one. So, it is behave like this. Another piece from there may be having the difference in their density. Okay. So, and within this essentially we are considering that the charge is uniform. So, that is why this is called the uniform electron charge, okay, or unified electronic charge method, or the uniform electron density method. It is now possible to calculate the exchange coordination energy for each electron within the electron density with the electron density that is assumed to be constant in that piece. So, if the electron density is constant, so from there we can easily find out the exchange energy of the electron. Okay. The energy also associated with these local element can be summed up to equal the total exchange energy. So, that is essentially the local. Local means we are taking a very small piece of it, or there is a small region of it, and we are saying that within this region there is no change in the density, and we are just there is n. So, if the density is not changing, so essentially for that small piece also we can find out the exchange correlation function. So, the LDA adopts a homogeneous electron gas system. Electrons are distributed evenly with a uniform positive external potential, and the overall charge neutrality is preserved for the construction of the exchange correlation function. Okay. The exchange energies for electron or the potential function with the electron density can be specified in a simple analytical form. So, this is one of the analytical form. So, the rho to the power of 1/3. Okay. So, similarly, if you just take the operator, the exchange operator as rho to the power 1/3. So, essentially the energy as a functional form should be equal to the C into the rho to the power 4/3. Okay. So, with this approximated potential, the self interaction portion of the Hartree energy will be largely but not completely removed, and this incomplete removal of the cell interaction will cause some problem and error such as the undetermination of the band gap. Okay. So, essentially it does not give the proper band gap. Okay. The coordination energy for a simple homogeneous electron gas at the high density limit at Rs less than 1 and given by again some of the parametric function it is used. Okay. Where Rs is the radius of the sphere containing exactly 1 electron, or we call the Wigner-Schilz radius related to the electron density as 3/4 pi rho r to the power of 1/3. Okay. So, this is some of the functional form we are using for finding out the correlation energy, exchange correlation energy. Okay. So, in the case of the generalized gradient approximation, in not only the charge density, we are just writing the gradient of the charge density also. So, that is why this is called the generalized gradient approximation. Okay. So, in principle, GGA or generalized gradient approximation should return better result with the general formula with density gradient as an also additional variable. So, essentially also not only the density, we are using the gradient of the density as also as a variable. That means we are writing this function the functional form also in terms of the sum of the mathematical operation to the gradient of the density. Okay. Like here it is shown. So, when the energy functional is in this integral form, the general form of the potential will be, of course, it will have all this the exchange the GGA case, you will have the density, at the same time also the gradient of the density. So, we are writing in terms of the dPPR also. So, considering the spin variable, the expression for GGA energy function also, it will have the need to consider all the spin also. The general form of GGA is expressed based on the LDA with an additional enhancement factor or Fs, and this Fs factor also we can write it like this. So, essentially it can approximate gradient. If you use GGA, then it will better approximate the exact charge. Okay. So, let us say the actual charge density at a maybe something like this, and at a particular LDA may be behaving something like this, and GGA will have, because in the LDA there will be no change here, no. But in the case of the GGA, within a position also there will be change. So, essentially this approximation is better. So, overall case, so these are the all different approximation we need to get in order to get all the different terms, and having all these terms, now again you need to use some of the variation principle to get the energy equation, which we can solve, so that we modify the charge density, and also we modify the energy so that we go to the ground state level. Okay. So essentially we use again the variation of the energy function and make it to 0 at equilibrium. Okay. So essentially I not go the details to it. Essentially what we get is something like this minus of psi minus half del square plus u effective minus ei into psi I. So this is for each of the electron in the density function theory, and this phi I are nothing but the Kohn-Sham orbital. Okay. So this is called the Kohn-Sham equation. So you will get n number of for n number of n electron system, you will get n number of this Kohn-Sham equation. Okay. And this equation now we solve it iteratively. Okay. So essentially Kohn-Sham equation is in the form of as a familiar, it is again looks like a Schrödinger equation with the corresponding Ks Hamiltonian. So this is the Ks Hamiltonian effective and this phi. Now within this effective also you need to see all those the external potential, Hartree potential, exchange and coordination potential, and within the exchange and coordination potential you need to do either LDA, GGA or hybrid, and for all the cases again exchange coordination function you need to use the exchange functional. So that functional is not known, and for there you can use the AIML method also. But there are certain the number of functionals are going nowadays. Okay, you need to check which function the position only. Okay, the orbitals psi r are the solution of the Ks equation and are now named as Ks orbital. Eigenvalues, these are eigenvalue for each electron. So or it's a kind of a Lagrange multiplier is equal to del psi del OR, which is equivalent to the chemical potential, and the highest occupied state is equivalent to the exit ionization potential, and Ei represents the energy of each case electrons, and their sum becomes the total energy after the double counted errors are removed, and qualitatively describe band structure, density of state, bonding characteristics and all. Okay, so that is essentially the scheme for DFT calculation. The method is something like this. So first you create the trial density. So trial density again you get it using some of the basis function to find out the trial density. Okay. At the same time also you need to give the functional form of the exchange coordination. These are the two input only. Okay. So this is not known. Okay. But there are certain standard exchange coordination functionals are there that will give it. So that first you calculate the Kohn-Sham Hamiltonian. Okay. Then you solve the Kohn-Sham equation for each of the electron. Okay. So you get n number of solutions. So and now during the solution itself, now you change this the density. Of course, the density is changed due to by changing the parameter of the basis function. Okay. Then you get the new basis function, and from the new basis function now, or sorry from the new kind of, so you get the new kind of these orbitals. Okay. From those orbitals now you find out the new density. So this density will change. Okay. Now you see, now you calculate energy. If the energy is calculate, so this one you are doing this kind of the going down the energy and finding out the density, and if it's converged, that means if there is no change in the density in between two successive steps, then we can calculate the forces and update the ion position. So this portion we call it the kind of this the stationary calculation. That means we are just changing the electrons for a particular set of electron nuclear position, and then from there also you can get those. Now we can change the ionic position so that we get lesser energy, or we can go for the geometry optimization, and geometry of change the electron nuclear position also there will be change in the density. Okay. Then also you go for again evaluate the new case with a change in the nuclear position. Okay. Then if it's converged, then we can say that we got the kind of the equilibrium structure. Okay, that means the position of the nuclei is such that the total energy is less. Okay, but first thing that for a particular set of nuclear position, first we calculate the electronic energy, which is called the single point calculation. Okay, and then you modify the Kohn-Sham orbital so that you get the modification in the density. Okay, and then you see that whether when the density remains same between two successive iteration, then we say that then we got a kind of a stationary point. Okay. Then we modify the nuclear position, and by that way also we go for the geometrical optimization. Okay. So this is essentially the overall flow chart for calculating the density functional theory. Only input is that is the trial wave function, trial density. Again, this trial density comes from the basis function. Basis function is known. At the same time, also you need to give the functional exchange correlation. So, of course, there are not only the approximation in terms of this interacting, non-interacting, exchange correlation potential, and the basis function for finding the density. There are other approximation also you need to do to cut short the number of electrons, at the same time also to cut short the number of atom you need to treat. Okay. So, let us see. Density functional theory has extended not only to crystalline solid, but also to glass or amorphous and minerals such as zeolite, polymers, even DNA, ice and chemical solutions. Two obvious issues have to be resolved. The number of electrons become infinite, and so does the number of atoms in the solid, and we need to first eliminate the large number of electrons from calculation by using pseudo potential. Pseudo potential means essentially we eliminate the effect of the core electron, because most of the reactivity or the structure determining electrons are the valence electrons. So we just consider only the valence electron, but we approximate the core electron with a very simple function. Okay. So this, in order to decrease the number of atom you need to deal with, essentially we go for the periodic boundary condition, what we have dealt in the last class, and also supercell approach. And within the periodic boundary condition also, system size is further reduced and transferred to a reciprocal lattice by the use of the Boolean zone construction and k-point sampling. Okay, this is also another method where also you can decrease the number of atom you need to treat. So it should be less than the whatever in the unit cell atoms. Okay. The Gauss theorem also we can use. Fourier transformation and plane waves expansion methods are used to represent the quantities on each of the k points. Okay. Calculation is carried out back and forth between the real or direct and reciprocal space or k space, depending on the calculation efficiency in each spaces. And some practical topics directly related to the actual DFT rounds are the energy cutoff. Again, as we have done for the case of the DFT case, also energy cutoff. Here also we need to look for the energy cutoff, number of k points need to take, or the integration rules, and also the this smearing or smoothing of the charge. Okay. So those are the practical consideration for further approximation required in order to treat a real system comfortably. Okay. So that gives you the overall view of the density functional theory. Hope you have learned little bit of the density functional theory. I have given you only the basic principle behind it. There are a lot of things to deal with the DFT method. There are new modifications are also coming. So far what we have dealt with the ground state. Nowadays density functional theory also can be used for excited state. Even also it can be used for time dependent case and all these things. Okay. So I'll stop here. These are the good reference you can follow. Thank you.